Do you remember these blocks from kindergarten? They're called base 10 blocks, or Dinez blocks, after some Hungarian teacher from the 1900s. It's a system of 4 types of blocks, which I'll call the cube, the stick, the square, and the chunk. You add them together to make different numbers. The stick represents 10 because it's made of 10 cubes. Similarly, the square is 100 because it's 100 cubes, and the chunk is 1,000 because it's 1,000 times the volume as a cube. It's really just a nice way to show base 10 to kids and have them learn how to add. For example, 135 is a square, 3 sticks, and 5 cubes, making 1 times 100 plus 3 times 10 plus 5 times 1 is 135. And you can do this for any integer up to 9,999, provided you have enough blocks. Technically, you can have more than 10 chunks if you ignore our base 10 rules, but that's not really good to teach children. You can add numbers by just putting them next to each other. You can simplify if you want by packing into new units, but it's mathematically the same thing. Let's say a block with n cubes is a block of size n, and the set of block numbers is the set of numbers that can be represented with the current amount of blocks. The Dinez blocks have block numbers from 1 to 9,999. But just look at this. It's great for showing children how to count and add, but it's so inefficient. If you want to express a number like 6,968, you need a total of 29 blocks, which is way too many. So if you had to recreate these blocks to minimize the amount of blocks needed to represent a number, how would you do it? Let's say we want to find the smallest set of blocks so that we can create every integer up to our target, which is 9,999. We don't care what shape or arrangement each block is, only the amount of cubes in that block and the amount of that block needed to make the block numbers. All blocks of one size are different, but the size of each block doesn't matter. It always counts as one block. And we're already reordering these blocks, so we can safely say that we don't care about using these for children's education, so we can have as many of one block type as needed, and the block size can be any positive integer. To solve this, we need to look out for the extremes. For example, 1 can only be made if at least one of our blocks has size 1, since you can't break it down any further. Now we need to make a 2. We already have a 1, so we can either add 1 to our blocks, or add a 2, which automatically represents 2. If we add the 1, then we would only add 2 to the block numbers, but adding 2 to the blocks gives us 2 and 3 in the block numbers. Then it's obvious that we should pick 2. There's another cool thing about these block numbers. If the block numbers contain every positive integer up to n, that is, if the integers 1 to n are a subset of the block numbers, then adding m plus 1 to the block would make the integers 1 to 2n plus 1 also a subset of the block numbers, because you can just add any integer from n to that n plus 1. And we can currently make from 1 to 3, so it would make sense for us to add 4 to our blocks, giving us from 1 to 7. Then we can add 8 to the blocks and making the numbers 1 to 15. We can add 16 to go up to 31. And now we see a pattern. If we add the next power of 2, we get every positive integer up to the next power of 2 after that, minus 1. Then it's settled. We just have one of each power of 2 as our blocks. For 9,999, we only need up to 8,192, which is 2 to the 13th, because we also need to keep 1, but the blocks require 36 total, which is way more than we have now. But how do we know that 14 is the absolute minimum? Well, look at the subsets of any set of n blocks. To pick a subset, each block can either be chosen as an element or a non-element of that subset. There are 2 ways to include or not include each of the n blocks, so there are 2 to the n total subsets. Assuming each subset adds up to a different number, which we can make with careful selection, you can represent 2 to the n different numbers. 9,999 is a little over 2 to the 13th, so a 13 block set won't be able to represent all the different numbers. There'll always be a couple missing. Therefore, 14 is the minimum of a block size set. And there are many different sets that do work. It's just that the binary powers of 2 make the most sense for expanding this upwards. Notably, the powers of 2 don't ever repeat a sub, which makes sense because of binary. So there you have it. Binary blocks are superior to base 10 blocks. Just don't use these blocks to teach kids how to count.